What's up, ninjas, and welcome back to the channel. Ever wonder how your computer can stream music, run a dozen browser tabs, and download a game all at the same time without literally catching fire? Well, it's not magic. It's actually a masterpiece of digital traffic control called CPU scheduling. And today we're going to break down exactly how it works.
Okay, let's dive right in. It all starts with a pretty basic problem. You've got tons of tasks you want to do, right? But you only have a few processors to actually do the work. The whole goal is to create a system that feels totally seamless and lightning fast. And to do that, the operating system scheduler has some very clear objectives. You know, it's this crazy balancing act. On one side, you want to maximize CPU utilization. You want that processor working hard, never just sitting idle. And you want to maximize throughput, which is just a fancy way of saying get as many jobs done as possible. But then, on the other side, you absolutely need fairness. You can't let one huge program just hog everything and grind your whole system to a halt. And finally, you got to respect priorities, so the super important stuff always gets to jump to the front of the line.
So, now that we know why we need to schedule everything, let's get into the how. How does the operating system actually pull this off?
This right here, this is kind of the secret life of every single program on your computer. It's not just one constant sprint to the finish line. Nope. It's this cycle of working and then waiting. The work part, when it's crunching numbers and doing calculations, that's called a CPU burst. And the waiting part, when it's waiting for you to type something or for a file to load from your hard drive, that's an I/O burst. And it just goes back and forth over and over again. And that cycle leads to this really critical distinction for the scheduler. You've got CPU-bound processes, think of rendering a huge 4K video, that are just pure calculation. And then you have I/O-bound processes, like a word processor, that spend most of their time just waiting for you. A good scheduler has to mix these two perfectly to keep everything running smoothly. A bad mix, well, that's when your CPU is just sitting around twiddling its thumbs, waiting for the hard drive to catch up. So every process goes through these different states. And the scheduler's whole job, its entire reason for existing, is to decide which process gets to move from the ready state to the running state. It's basically the bouncer at a club, deciding who gets past the velvet rope and onto the main stage, which in this case is the CPU.
Now, think of it like this. Non-preemptive scheduling is like a chef who has to finish making one dish from start to finish before even looking at the next order. But preemptive scheduling is like having a head chef who can pull that cook off the line to immediately handle a dish that's on fire. It's no surprise that basically all modern operating systems are preemptive because it makes them feel so much more responsive.
And the dispatcher, this is the real unsung hero of the whole operation. It's the module that does the actual handoff. This is called a context switch. It saves everything the old process was doing and loads up everything for the new one. And this has to be blindingly fast, because every nanosecond the dispatcher spends switching is a nanosecond your computer isn't doing actual work.
All right, theory is great, but let's see this stuff in action. It is time for an algorithm showdown. We're pitting two classic scheduling methods against each other. First come, first served versus round robin.
First come, first served, or FCFS, is exactly what it sounds like. It's just a simple line. First one in, first one out. Super straightforward, right? It's fair in one sense, but as we're about to see, it's not always very efficient.
So let's set the stage. Imagine three processors show up in this order: P1, then P2, and finally P3. And these are their burst times. That's how long they need to run on the CPU. As you can see, P1 is a really big job, while P2 and P3 are super quick.
Okay, check out this Gantt chart. It shows exactly what happens. P1 gets the CPU first and runs for its entire 24 milliseconds. That means poor P2 has to wait 24 milliseconds just to start, and P3 has to wait a full 27 milliseconds. If you average that out, the average waiting time is a whopping 17 milliseconds. That's not great. And this reveals the huge, glaring flaw in FCFS. It's called the convoy effect. It's like being stuck in a single-lane tunnel behind a giant, slow-moving cement truck. Everything just grinds to a halt behind it. So, can we do better?
Oh, yes, we can. Enter round robin. This is a much smarter, much fairer approach. It's preemptive, and it gives every single process a small slice of CPU time, so those big, long jobs can't hog all the resources.
Now look what happens when we run the exact same processes through round robin, but this time with a little time slice of 4 milliseconds. P1 runs for just 4 milliseconds, then it gets paused.
P2 jumps in and finishes its 3 milliseconds. Then P3 jumps in and finishes its 3. Then we circle back to P1 for another 4 milliseconds, and so on. The short jobs finish super fast, and when you do the math, the average waiting time plummets from 17 milliseconds all the way down to just 5.66. That is a massive improvement.
And this right here highlights the key trade-off. See, the magic of multitasking isn't really doing things all at once. It's about switching between them so fast that it feels like they're all happening at once. So while the total time to finish that big job, the turnaround time, might be a little longer with round robin, the system feels way more responsive. You're not left waiting. Every program gets a little bit of attention quickly, and that's exactly what you want for a great user experience.
So how do we actually, formally measure which algorithm is better? And what about those special situations where just being fast isn't nearly good enough?
Well, to properly compare all these different algorithms, computer scientists use a few key metrics to keep score.
First up is turnaround time. The easiest way to think about this is it's the total time from the second you click to launch an app to the second it fully closes. It's the process's entire lifespan in the system.
And then we have waiting time. This is a bit different. This only measures the time a process was totally ready to go, but was stuck in line waiting for its turn on the CPU. This is the number we really want to shrink to make a system feel snappy and responsive.
But then, what about systems where a deadline isn't just a suggestion, it's everything? That's where you get into the world of real-time scheduling. And this isn't about being fast on average, it's about absolutely guaranteeing, a result before a critical deadline passes.
I mean, just look at the systems on this slide. A car's airbag system, an anti-lock brake controller, a medical pacemaker. For these things, a delay of even a few milliseconds isn't just an inconvenience. It could be catastrophic. So for these systems, it's not about average speed, it's about the absolute rock-solid guarantee that a task will finish on time every single time. It's all about predictability. So which one does your computer actually use? Well, modern operating systems like Windows or Mac OS use a really sophisticated mix of algorithms, usually a priority-based, preemptive approach that's a lot like round robin, all designed to give you that snappy, responsive feel. The next time you're multitasking like a pro, you can thank this incredible, invisible juggling act happening under the hood. So, what do you think? Let me know your thoughts in the comments below. And hey, if this deep dive helped you out, do me a favor and smash that like button. Subscribe to Cyber_Ninja for more, and make sure you ring that notification bell so you don't miss the next one. Keep learning, ninjas.